Having me here. My name is Bob Kelly and I appreciate the opportunity. Like the rest of you, I find this work to be challenging and fascinating, of course, but there's so much to learn in this field of exteriors. After the building boom, it seemed like all of the residential new construction buildings, the focus of our work has been retrofitting and repairing residential structures. They all had efflorescence on them, and I admit, at the time, I didn't understand the cause. But if I base my opinion on the buildings that I've taken apart, water management seems to have been somewhat of an afterthought. Now, after experimenting with nearly 200 buildings and seeing how they've gone through a drying mechanism, I want to share what we've learned. Anyway, let's first preface this conversation with, I'm not blaming anybody for the problem because there are so many coincidental factors that happen in this space. Failures is really kind of a strong word, but many problems that we've seen are from the effects of creating an airtight structure. When you see the world through my eyes, the problem presents substantial challenges to the owners of these buildings. So masonry parapets covers a wide range of topics. Roof terminations, copings, both metal and stone, lumber bearing within the wall, and sheet metal to shed water, just to name a few. A number of issues can happen in this area. So parapets are prone to moisture accumulation through stack effect, capillary action, and just bulk rain. And there is the fact that vapor-laden air is lighter than dry air, which these buildings really fill up from the top down. Then there's condensation from lack of air sealing, which was taken into account that almost none of the buildings I've encountered have ever been air sealed. So condensation truly forms from the layers of roof terminations, the roof membranes, masonry, sheet metal, and carpentry. The moisture-laden air is always trying to escape the building. Well, this particular building here is 9 years old. So years ago, when I was working alongside another roofing sub, this before I got into this, we pulled back a roof membrane, and I would ask these questions like, why is the roof always wet behind the membrane? And the answers I received time and time again were, it's always wet. Well, that didn't really sit right with me. This building here, this really grabbed my attention when I was driving down Damon Avenue one day. This building was only 15 years old. So how can this problem be such a common issue in such a massive industry? Its buildings need to dry to be healthy, period. Lstriburek of Building Science Corporation calls this syndrome Parapetitis, sick parapets. So today we're discussing how building materials have changed, assembly methods really have not, and how this affects the building envelope. This building here we just fixed is 18 years old. About 15 years ago, a home inspector friend pulled a loose capstone off a 5-year-old building in Lincoln Park and got hit with a blast of hot, wet air. And this prompted us to experiment with ways to dry out the parapet because at least we knew dry means healthy. So at the time, there were no products or methods to address this problem. So initially, we gathered materials to vent the parapet and to create a gap under the capstone on top of the wall so that air would at least blow through and create some drying effect. I knew that we had the problem isolated, but we didn't have the solution yet. So how do we keep out of wind-driven rain and let vapor out at the same time? So we looked at roofing materials, specifically ridge vents. First of all, we knew the fabric from a rolled ridge vent, which is called spun-bound polypropylene, allows vapor through but not bulk water back in. So we bought several rolls, probably about 30 rolls of this rolled ridge vent material, and we took it off the back of the ridge vent material and glued it to the top of the wall. And then on top of that, we installed pieces of corrugated plastic, which is a hollow plastic substrate. And then we put flashing, sheet metal, and eventually glued the stones on top of the wall. So once the limestone is set, and bed of polyurethane sealant, and then as far as the roof termination is concerned, we separated the roof membrane with a piece of plywood and a rain screen and tangled mesh, and then capped it off with a regular counter flashing like a sheet metal umbrella. The net result was the mold smell left the house. We gave it some air. So we have 6 parapets on buildings of all ages. because water vapor always rises to the top and is trapped by the same membrane that's stopping water from coming down. With air escaping from the interior, there's always going to be condensation. So we know historic masonry buildings were made from soft, low-temperature, fired clay brick and lime mortar with no Portland cement, and that's the key, no Portland cement. There was no flashing or insulation, but the building envelope was able to dry outward and inward to remain healthy. Parapet walls were still needed to be rebuilt. At the time, I thought old parapets getting rebuilt was a function of an old building, but that's really not what happens. It's when the water vapor rises up, it washes out the lime. And here's a good example of what happens when parapets are wrapped with roofing materials. They get wet and they stay wet. So this picture is really interesting to me. At one point, I was driving around taking pictures of buildings just as the rain started. And one thing I was noticing was that the parapets always showed wet before the rest of the building. So this shows that the building is already saturated and vapor-laden air is lighter than dry air. There's buoyancy. So this building here is less than 20 years old. So let's talk about changes in materials. Our mortars are getting harder, which means hairline cracks are prevalent. Portland cement is akin to an epoxy additive to make flexible lime and sand set up quickly so we can build faster. But when we talk about mortar, this slide can be confusing. Suppliers only print the minimum strengths in their literature. You need to know that the actual 28-day cured strength to specify mortar correctly. For example, type N mortar is listed at 750 psi, but the cured strength is actually 1800 psi. All buildings built pre-1930 in Chicago were built with lime mortar, which has an average cured strength of 750 psi. So FYI, to get the actual cured strength of the mortar, refer to the manufacturer specs. And of course, the most common type of mortar in our market is type N mortar. But don't get me wrong, after buildings are built, Portland type N and type O mortars have some breathability, but they just dry much slower than a pure lime mortar mix. Now here's a slide of both pure lime mortars and Portland cement mortars. The pure lime shows gaps in between the lime molecules, allowing for drying. But when the lime gets wet, it dissolves slightly, healing the cracks in the building, called autogeneous healing. On the right is Portland cement, which is a crystalline structure and has triangular shapes fitting tightly together. Being harder, it does not dissolve, which leads to hairline cracks, thus changes the prefix from adsorbing to adsorbing, a surrounding of moisture. In the next three photos are buildings built of precast stone. This material is engineered to be porous, at least the materials that I've come across. It is often used as a cheaper substitute for limestone. This building was only 22 years old. The simplest way to identify precast is it's clean. It doesn't have the ability to hold moisture, whereas limestone does, and that helps to promote algae growth. So when you see dirty limestone, there's something growing in it. When I see precast, I often just, when I go to bid a job and someone wants the building sealed, I tell the people that I can't be successful sealing a building that has precast, not 100%. And as you know, this is what the industry would be calling a reservoir cladding. We often find pools of water in the masonry as we're taking it apart. Here's another reservoir cladding. This is a split-face block garage that we were taking apart. We pulled the capstone off the top of the parapet wall, and I admit, I looked down and I saw a column of water, measured down to the bottom of the column, drilled a hole, and out came, I think, more than 5 gallons of water. It poured for several hours. Now let's look at the wood. Our original wood supply was ancient, and it was full of resin. And when you cut into old lumber, you can smell the turpentine in the sawdust. In fact, you can identify what kind of lumber it is by the smell. I would consider this a fairly typical cut of an old growth log. So turpentine is antibacterial. Pinene and other terpenes disrupt microbial cell growth, and historically has been used as a natural preservative. So we have entered into a new era. Our world is dependent on quick growth lumber. And why do trees have more resin than young trees, old trees versus young trees? Well, it's a simple answer. There's more growth cycles and more deposits of resin. And does a young tree work as well? Well, no. The answer is flat no, because there's very much less resin, and it's all pulp that's being susceptible to fungi and insects. So back in the day, I started out as a carpenter. I consider myself a carpenter to this day. When you go to the lumberyard, there might be only 2 or 3 bad sticks in the bunk. It was all quarter sawn, fir. Well, now you go to the lumberyard, and there's really only 3 or 4 good 2x4s in the bunk. So contemporary building issues. So modern masonry is definitely harder and less absorbent. And masonry does store water. And modern wood is definitely softer and less durable. And engineered lumber, you gotta be careful with it because it definitely degrades quickly when exposed. And the fungus eats the sugars in the glue, loosening the OSB bond. There's a gentleman by the name of Jeff May who has written several books on the topic. One is called My Office is Killing Me, and My Home is Killing Me. I suggest reading. So the water problem equations. So old buildings had softer, breathable masonry and resin-rich lumber. And that creates a very long-lasting building, but modern buildings, at least in the residential market, it's definitely harder masonry and soft wood ends up having a wet, easily compromised structure. Now the next part of this equation is hillstock insulation. There's 2 types, vapor open and vapor closed. Vapor closed, of course, is foam, vapor open, cellulose, fiberglass, rock wool, and real wool. Buildings that we've opened up with foam insulation end up looking like this. I'm not finding fault with foam. There's an application for all these products. But the problem that we see is the effects of positive pressure in a tight envelope and a lack of dehumidification, coupled with poor water management on the exterior, makes these buildings nightmare to deal with. These photos are from the same building. In the morning, we pulled off the flashing and put on a venting system. It was full of ice, frost, and as the day progressed, that was melting and splashing on us. And so most buildings typically have a sealed flashing. The wall can be dried out, even if it's grouted solid. Moisture will come through the solid bond beams in the buildings. So in these next 2 photographs, when we pulled off the capstones, we found often that the flashings were cut short. It shows 2 things. One is the masons didn't understand the use of flashing, and second of all, that old school masons are trained to have a mortar bond gluing the layers together. In effect, what really happens is that these flashings get cut short, water goes through the limestone, goes around the flashing because the mortar is blocking the path out, and it goes straight down into the wall. This is my hygrometer reading 100% moisture on a foam cinder block building, and here's the building. This is a photograph of the same building at 5 below. You can see all the vertical reinforcements are holding moisture and frosting as a result of the cold. Still stunning. So as you know, water goes through mortar joints, it goes through limestone sills, and areas that don't have the proper flashing and water management, it's just going to continue to create mold and rot in these structures. There's another split-face block building that was never sealed. I think it was probably the most saturated structure I've ever seen. These next photographs, you can see the TJIs, which should have never been set in split-face block. At the very end of these joists, you can see the
The web is rotting, and then of course the steel is shot. That building was only 19 years old. And I'm sure you've seen plenty of rotten sheathing in your time. So this is something that we're starting to see on an almost daily basis. Rotten trusses, because the trusses are grouted in. I believe the code says to grout all wood trusses. Now the problem here exists that now, for sure, water is going to get transferred through the mortar and directly into the lumber. I've got some more examples of rotten trusses. In fact, we just opened up another building last week where half of the roof system should be replaced. And in fact, we're going to have to build a whole new roof system that'll hover over the top of the old stuff because they just simply can't afford to have it done properly. Foam adds to the problem of grouted and bedded lumber. Not only does it make sure that it's in direct contact with the mortar, but when you've removed any chance of the building's ability to dry inward. Now in this next series of pictures, this is not fire damage. This is mold and rot. This building, this 15-year-old structure, had open cell foam injected into the ceiling. Open cell foam has the ability to hold a very large quantity of moisture. There's a paper written by a building scientist who works with Lstriburek, his name is Foster Lyons. It's called ping pong water. I'd highly recommend looking it up. The insulation at the perimeter gets wet, it stays wet, and keeps moisture in direct contact with the trusses, plywood sheathing, etc. Now here's my lead carpenter pulling open cell foam out of the structure. This is what real life looks like. This 15-year-old roof system had to be completely removed. So jobs this complex require time to fix, and they need full protection from the weather. This is where, outside of our venting system, we had to develop a tent because we had no other choice. In order to remove or repair trusses, we had to figure out how to completely cover a roof to do 2 to 3 months worth of work so we can see everything at once. Our tents will last 3 to 4 months because the UV protection, we've had them up for several more months than that, 6 months, but the rating should be around 3 to 4 months. And we've been able to withstand 65-mile-an-hour wind gusts and rain and snow. So here's another project with removed trusses. We had to suspend the air conditioners. Also, we build custom tents for several different types of architecture. Different kind of balconies, roof overhangs, and other interesting architecture. So now, one case study I present is we call it the Greenview Spray Foam House. The homeowner called us because humidity levels were high, with leaks in areas they couldn't stop. It was originally built with fiberglass spats in the walls and roof, but they had rotten trusses, so when the trusses were replaced, 4 years prior to us being there, they were retrofitted with foam in the 3rd floor balcony roof. The garage also has some water issues, as you can see on either side of the railing there. So first, we tested with Rylan tubes, and you can see how much water this building is able to take on. Pretty typical, I hate to say it, but it's typical. So we installed our vented flashing system. We grind off the top of the wall. We also grind the mortar from the bottom of the stones as we install our flashings. We set our flashings in polyurethane sealant, so we glue between the layers. Our preference is Seco 1A. And when we're done, you cannot tell that we have a vented system in place. As we explored the roof of this property, we found rotten trusses. So now we're going to walk through the process of repairing the trusses. So first we build a tent, and the following steps are for most truss reinforcement and replacement projects. So we removed the insulation in contact with the masonry and the truss ends. In this project, we didn't have to pull all the insulation back because I did moisture readings, and then the moisture readings in different parts of the building were between 13 and 18%, so I didn't want to rip anything out if it was being useful. So keep in mind that the water source is always the masonry, most always the masonry, but the foam holds the water against the trusses when in contact with the masonry. It doesn't mean that I endorse the use of foam, but in this case, it did not pose a threat. We were able to save the money, save a lot of money for the homeowners. So these were existing conditions. Somebody 4 years prior put some 2x4s alongside that helped reinforce it, but it didn't do anything. So unfortunately, the engineer we hired for this job figured that we only had to remove 32 inches of foam to reinforce the ends of the trusses. So what we do is we block out the ends of the open web trusses and then laminate 3/4 structural grade plywood nailed and glued to both sides. And then as we prep for the installation of our brackets, we use the Hilti epoxy system in this project. You inject the epoxy, put in the netting, and then we bolt the brackets up against the wall, and then we use some high tensile strength screws to mount the brackets into the solid end of the trusses. We're basically converting a top hanging truss to a bottom bearing truss. Here's the finished section of the floor before we installed cellulose insulation. So the green up against the inside of the parapet wall is really just simple dimple board. So I always want to separate the insulation from the inside of the masonry before we blow in the cellulose. In this case, to make sure that we were able to get any kind of vapor out, is I cut the plywood sheathing into strips. Then we go over the strips with, I don't have a sample here yet, but I've got it at the table. It's dimple board laminated to high density polyiso. So now we've got an engineered 3/8 inch gap where any kind of vapor that's coming through the plywood, the joints, the nail holes, and especially around the perimeter, it comes out and then gets sucked out the inside edge, inside face of our parapet wall. And I'll show the drawing in just a minute. So basically it's a horizontal and a vertical raised ring that we developed. The net result in this job, the reason why I showed the trim in the house is because that molding was actually down 16 feet from the vent. In this case, we vented the the penthouse of the house first. And then the next spring, we flashed all the parapet walls in the lower balcony. So over the winter, water went horizontally. This was the furthest point of the roof from our venting. It went 25 feet and then up 16 feet. So the homeowner asked me, he said, do we really need to install the venting in the lower balcony if this is happening? And, well, we went ahead and did it. But you see, this is just from one season of drying. And these trusses were only 4 years old. So how do we really fix a building so that it doesn't become saturated again? We use wind pressure and uplift. So we commissioned a wind study, a computer simulation, where we found out that when the wind is blowing through our flashings, the greatest amount of pressure is when it hits the top of the wall and it flicks back. Originally, I thought that the greatest amount of pressure was when the wind came over the top of the wall and created an eddy down below, but in fact, we use this wall as the example. It hits here, it pulls back, creating suction on the leeward side. Love this picture. This picture is when we install our venting system on top of an architectural brick facade. I'll turn this for you, if I can. That's okay. The efflorescence was forming at the top of the wall at the vent. Now, being the first time I noticed this, at least this shows me that my venting is working actively. So here's how we fix these buildings. We create a thermal break between the masonry of both the roof and the top of the wall membranes. These are prone to sweating. So when the air flows through, it creates negative pressure and pulls moisture out of the structure. The following parapet drawings are all based on the same theme, taking advantage of stack effect, capillary action, lofting vapor drive, and negative pressure and wet to dry effects. So this definitely jumpstarts the drying process. So we can see that we separate the roof membrane, so the thermal mass is not connected to the thin membrane because the two change temperatures at a different rate. And then we have our corrugated plastics that create a rigid, hollow extrusion so that when the wind blows through and creates suction, drying the moisture out. So vented flashings keep out both water and allow for drying. Now, let me go back to this picture of the clay tiles. So what we've been doing in this situation, it's actually very interesting that we would take a piece of corrugated plastic, the sheets are ripped at the 4-foot way, and we plow them out on the very bottom. And then we cover the wall with a vapor-open fabric. This fabric has a perm rating of 108, but yet it holds the surface tension of water. So we glue this down, like so, and then roll the fabric out. We put a bed of polyurethane sealant on both sides. We glue the fabric down, and then when it comes to setting the clay tiles, we'll have 4 blobs of caulk, no other way of saying it, and we glue the clay clear tile onto the wall, and then we caulk the bell with baccarat and polyurethane sealants. It's been very effective. In fact, the first time we did this experiment, the building was a 3-story residential property. It must have been about 100 years old. They used spray foam on the interior of the building, and they repointed the exterior with Titanium mortar. So they were trapping moisture on both sides. So we did that process, and a couple months later, the homeowner calls me and says that the casings on the side of the house, exterior of the building, they all warped off the walls, and he could smell a rotten, moldy smell behind the casings. Well, in fact, what happened was when we created a drying effect, all the moisture raced to the roof and came out of the house. And a couple months later, the mold smell left the building. The air conditioning had shut down. And after we did this process, the air conditioning came back on. That's how saturated the building was. So we've applied this theme to every structure. I'm trying to save the building materials. I mean, I don't want to look at a building and say, oh, that's what I'm hoping. Maybe we need a new one. So trying to utilize the materials that we have. On parapets with metal copings, we do remove the wood nailer and then fasten the copings directly to the masonry with rigid hollow spacer for air to flow through. It's important to make sure the top of the wall is exposed for full drying effect. We also install venting into the roof cavity to exhaust the water vapor. This flashing detail is so that our clients can enjoy the look of brick. So it's a shorter roof termination. Instead of bringing the vent panel all the way up to the top, which that's where the strongest amount of suction is, we do it down low, and it still is effective. It just takes a little bit longer for the building to dry out. Another application, brick and block with another coping. We've seen every configuration of terracotta, split face block, common brick, and so on. So this picture represents a victory for us. We're on a 10-story building that was about 80 years old in Milwaukee. As the installers were putting the vented flashing on, in the morning they could see steam rising out from the flashing. Now here's me installing our vapor open fabric. So just as a reminder, that fabric is it's got a perm of 108 and it holds the surface tension of water. But the thing is, when the wind is blowing through the flashing, the average wind speed in Chicago is 18 miles an hour. At 18 miles an hour, it will create a negative 7.2 CFM, putting the building on a constant draw, a gentle draw. You're not encouraging stack effect, just enough to get the moisture out, and it's all natural. Here's another example of parapet venting. This is probably our third building that we did, and the line between the top of the parapet and the material below, those aren't two different kinds of cinder block. It's actually the line between the parapet and the through-wall flashing. So it takes a little bit longer for the material to dry to the interior. So what we rely on is vapor open insulation. So when we have an interior rain screen and the inside of the parapet, that communicates to all the unsealed areas of the building, all the way down to the foundation. The moisture does go around the through-wall flashing. So okay, here's another picture of a building that we flashed in Uptown. We didn't do the roof, we only did the parapet wall. In this case, it dried down to the through-wall flashing, which that was the budget on this particular project. Okay, this is important information. These pictures, these next two slides. So the photos that you're seeing, this is wetness at the parapet. This has happened on a dry day. Now the picture on the left is a photograph my client sent me, and the picture on the right is one that I took. When we vent the wall, the pressure that's behind the moisture pushes the moisture to the surface. Now, I can't explain this. If anybody understands the pressure differences, I would like to have more clarity on it, but it's actually becoming a thing. Every time we vent the wall, moisture leads out of the building. It's a little bit difficult to see on the side, but this whole side of the structure, that building was soaking wet. So that it happened again. Now this is another project that we did, but this was near Tampa, Florida. What we did was we took corrugated plastics and we machined the plastics, a 2-inch stripe, lining up at every 8 inches, we had a 2-inch stripe. And we applied this to the inside of the entire building. And the concept is having, an engineered rain screen on the interior of the building. So one day, the homeowner is sitting on top of the wall, on the roof, admiring everything, and the back of his legs start to burn. So what we found out was that when we get solar drive, activating all the water, we turn the whole building into a linear teapot. Moisture was just coming out of the building instead of being driven into the structure. We actually dropped this cooling load by over 25%. Now, this next picture, I took this from about a block away. And this is 2 months after I did. The job was to only repair a 14-foot length of rotten plywood on the roof. But when we did that repair, I added vent. I wasn't even experimenting. I just thought, let's just install the materials and see what happens. Well, when I came back, I could see a 14-foot wide dry stripe all the way down to the foundation. So this next slide is a little bit of imagery work a friend of mine did who's a graphic artist. We didn't touch up anything. What he did was he crushed the colors in the picture, at least that's what they call it, which revealed the density differences in the wet and dry portions of the block. So it's similar to a thermographic image. Well, that was really, really cool. Now, another case study, this is a convent in Northfield. It's a 100,000 square foot facility, and we were working above the chapel. The mineral deposits on here, this building was built in 2000, and the mineral deposits were at least almost 3/8 of an inch thick. And this is from moisture rising from interior. So this chapel was a 50-foot diameter building and had curved limestone copings on it. And we pulled back a few stones, pulled back the flashings, it was soaking wet. So this is the process. We pull the stones, we grind the mortar off the top of the wall, we clean the bottom of the stones. And you can see that the designer put foam between the brick and the block. You know, I mean, that's a substantial thing to do. They're trying to, they use the best building science they know, but it still wasn't enough. So this is a photograph that, you know, we made radius copper edge metal for both sides of the structure. And in our shop, we made a template so we would take 4-foot sheets of corrugated plastic and machine them in that shape. So this is the corrugated plastic sheet, the same plastic that I had out in front. We machined about 4 stripes. Now, at this point, there is no science behind how many stripes do I put in there. What I did is I put enough openings in the bottom of the plastic so that I could still put enough sealant and glue it to the top of the wall. Then we took our inside and outside radius copper and connected it with copper strapping. And fixed it to the wall. Then we used textural flash, self-adhere flashing to seal the top of the wall, and then we set the limestone in a bed of polyurethane sealant, and we did use masonry anchors, very similar to what you see out in front here. As designers, you have the opportunity to lead by specifying repairs and innovative solutions to dry out wet buildings and keep construction dry. And parapet venting works. We've done it to over 150 buildings in Chicago. We've never had a callback. And for restoration of existing wet buildings, there are venting solutions that do help dry out the walls and slow any truss damage in progress. So this has been my life for the last 12 years, and I'm happy to share this information with you, and I hope that we can make the world a better place. So this is the end of our presentation.